All right, good morning. Really cool to have you. Last day of Chem 221. Whoa. Anyway, Lucas is going to give his class presentation now. So without further ado, Lucas, take the stage.
Hey guys, this is my element, palladium. Not much interesting to see on the first slide. Some basic facts. The symbol for the element is PD. Its atomic number is 46, and its atomic mass is about 106 grams per mole. Its electron configuration is krypton 4d10, and there's 6 common isotopes, with PD 106 being the most common at about 27%. It's part of a group of transition metals called the platinum group metals, that are all pretty similar in appearance except for osmium, and they all have similar catalytic, abilities or properties. And these are the other elements that are included, so that would be ruthenium, rhodium, osmium, iridium, and then obviously palladium and platinum. It was discovered in 1803 by a guy named William Hyde Wollaston. He was kind of an interesting guy. He discovered it he had this big batch of platinum ore, and he was working with it, and he was actually notorious for making a lot out of a little, but he still had a lot anyways. But he isolated it from the platinum ore, and he found palladium with the help of his buddy Smithson Tennant, and he tried to market it as this so-called new silver, but it didn't really catch on, as we don't call it new silver, we call it palladium. But I think you'd be happy to see all the cool things we use it for now. His partner, Smithson Tennant, was also pretty cool. He found iridium and osmium from the same batch of platinum ore. The most common application of palladium in our everyday life is in catalytic converters in cars. It converts harmful emissions like carbon monoxide and nitrogen dioxide into less harmful emissions like carbon dioxide and nitrogen gas. But it doesn't do it alone. It has some of the other platinum group metals in the catalytic converters to aid in the process. But that's the most readily available, applicable use. A cool field that it's used in is the medical field for a lot of different things, actually. In cancer treatments, it's used in a lot of medications, specifically for testicular and ovarian cancer, and it's used because it has some property that helps it bind to what I remember being quoted as biological targets. What that means, I wasn't 100% sure, but what it basically does is it helps stop DNA reproduction of DNA sequences that have the cancer in it, and it slows down the cancer, and it's pretty cool. It's also used in a lot of implants because it resists corrosion and oxidation. So it's used for that, and it's also used for stents and pacemakers and catheters because it has good electrical conductivity, and it makes it a pretty viable material for those devices. In the future, there's a lot of cool ways that palladium is likely to be used. Fuel cells, specifically hydrogen fuel cells, is one that I thought was really cool. I don't really know how often they're used because they're kind of a fringe technology, I guess, at least to everyday people. I didn't know much about it, but they seem like pretty cool and potentially viable sources of energy. And palladium is used as a catalyzing agent for the primary reaction, and that's pretty cool. And they're also used in solar panels. And as with most technology, more improvements are being made every day. So potentially palladium will be used more widely in solar. For emission reduction repurpose, it said that there was some breakthrough with palladium mixed with zirconium and some other stuff, like injected into the atmosphere, and that could potentially help with I guess it would be a redox reaction with some of the harmful greenhouse emissions into more usable compounds, which was pretty cool. As for that being super mainstream right now, I don't think it is, but it is potentially a use case for it, which would be awesome. And lastly, conductors and capacitors and all our computers, phones, cameras. I mean, it's used pretty readily in all technology. And as with the emission reduction and repurpose, there's more research being done every single day and more improvements for its effectiveness and efficiency are being made constantly. That's all she wrote.
Yeah, nice job, Lucas. Any questions for Lance?
Yeah.
Nice job. Well done.
Thank you.
Okay. Yeah, take the stage. Are you just going to talk or do you have a presentation? Yeah, oh great, go ahead.
Good morning, everyone. My name is Protein. I'm excited to be here to present my element, which is called zirconium. The zirconium has an atomic number of 40 and has the main three properties. The first one has the lightweight, durable, and corrosion resistance. The second one has high melting point and non-toxic and biocompatibles. The zirconium, let's jump with the background of zirconium. In 1789, discovered by Martin Henrik Krafthoff from mineral zircon. And the name zirconium derived from Parisian word zagon, means godlike. Yeah. Let's jump with production advance. The preferred zirconium first produced in 1925. Yeah. And also zirconium known for high strength and thermostabilities and crucial in advanced industrial applications like nuclear reactors and medical tools. Yeah. The production advance of zirconium. The purified zirconium first produced in 1925 by William Cross in 1940 made large-scale production more economical by using magnesium to reduce zirconium tetrachloride. Yeah. Let's go to the use and application of zirconium. Has the four main purposes and use of zirconium. First, zirconium used in nuclear industries, and zirconium used in medical field, and also used in aerospace and industry, and also used as a consumer product. Let's go to the future prospect of zirconium. It used in innovation in recycle. It used for innovation to reduce environmental impact, and also continue to demand in nuclear energy and advanced materials. And also zirconium plays a crucial role in industries requiring corrosion resistance, thermostability, and biocompatibilities. As the technology advances, zirconium's applications are expected to expand, driving further research and innovation. That was my presentation. If you have any question, you are free to ask.
Nice job, well done.
I appreciate for your attention.
Any questions on zirconium? Nice job. Thank you for coming. All right, give me just 1 second here. Shift over to thank you to both of you for presenting. That was really cool. All right, last day of Chem 221. Anyway, if you have any late work to turn in, I'm totally taking it. But that being said, I sure appreciate having you here and stuff this quarter. Very cool. What's going to happen next week? All right, we don't have 9 a.m. lectures Monday, Wednesday, Friday. We don't have a lab. So for those of you in Monday's Section 01 lab, I will see you only on Wednesday. Monday morning, you will receive an email from me with a link to the take-home lab final. And what you want to do is take that link, print off the lab final, and complete it. And then Wednesday morning, when I see you at 8:45 a.m. in 1303, this room, you will turn in the completed lab final. Also, the final exam prep worksheet will be due at that time. You can do that right now if you want. And you'll take the lecture final, all right? And the lecture final is a series of multiple choice questions, 4 short answer questions, stuff like that. Now, for you, I will see you Wednesday at 1:10 p.m. In 2501, the regular lab. But everybody else, this room, 8:45. Questions on any of this? Please know how much I appreciate all of your work on this. I know there's a lot of things going on and stuff, but we are just about there. So keep your eyes on the prize. Winter break's almost upon us. All right. So what we'll do is we'll do some more kind of review questions to kind of give you some ideas of the things to go through. We're going to start looking at some electron configuration questions. And this first one here is I'd like you to try and find the electron configuration for neutral chlorine, all right? So see if you can figure out which of those answers make sense. And we'll talk about it here in a little bit. Okay, so the whole thing with quantum mechanics was that they could figure out the energies of electrons. Because if you understand the energies, you can start making compounds, you can make the widgets that make people happy, whatever. And through quantum mechanics, as we talked about on Wednesday, the quantum numbers came out, NL, M sub L, M sub S. And from that, they finally realized that the electrons were placed in shells, all right? Now, shells are the first number, so like for 1s, 1n equals 1, that's the shell number. And for shell 2, there's 2 of these subshells, 2s and 2p. And again, you know that because the number literally is the shell. 3 there's 3 of them, 4, there's 4 of them, et cetera, et cetera. So at first, and this was Bohr's model, the hydrogen atom we did this week, they thought that energies were only based on shells. And for hydrogen, that works okay. But when you get to more than 1 proton, everything begins to break down. And so they finally realized that the N plus L values tell the energies. So this arrow right here shows the only orbital with N plus L equals 1. We saw how when you have an S, L equals 0. When you have a P, L equals 1, stuff like that. So you always fill in them in order of increasing n plus L. So what that means is the only n plus L equals 1 is first, 1s. 2s is next because that's n plus L equals 2. Here's a tie because 2p and 3s both have n plus L equals 3. So if there's a tie, you go to the lower one first, then the higher one, et cetera, et cetera. So the off-bow diagram, which I've drawn up here, is a great way to see how electrons are supposed to be put around atoms. All right, and that works really well for chlorine. So for this one, chlorine, what you need to do is first figure out how many total electrons there are. The periodic table will help you out. Chlorine is number 17. That means 17 protons, but neutral chlorine also has 17 electrons. So you can just start putting them in 1s first, 2s next, 2p then 3s, etc., etc. Now remember that s's always hold 2 electrons, p's hold up to 6, d's hold 10, f's 14, g's would be 18, stuff like that. So if you go through this, 1s2 would be the first 2 electrons, 2s2 would be the next 2 electrons, 2p6 would be the next 6, so 2, 4, 6, that would be 10 electrons to get there. 3s2 would be 12 electrons. 3p holds up to 6, but if you're counting, chlorine only has 5 more. So the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p5. And if you ever get lost on this journey, which is totally understandable if it's new, you can count the superscripts. So 2 plus 2 plus 6 is 10, plus 2 is 12, plus 5, 17. And that's how many electrons chlorine will have. So lots of different pieces of information there, but this is how then scientists find how many electrons are in the different atoms. You could write this in noble gas notation. You could write it neon in square brackets, not parentheses, but square brackets, 3s2, 3p5, because 1s2, 2s2, 2p6 is the neon configuration. And as the things get longer, noble gas notation can be pretty cool. Questions on any of that? Now, N plus L works really well most of the time, but on Lucas's presentation, I was like, oh, geez. Palladium, all the way to 4p, no problem. No 5s electrons. It was 4d10. And I was like, oh, geez. Okay, Lucas, make my N plus L rule look bad. But seriously, there are exceptions to this rule, all right? And if you knew on one of my quizzes, exams, whatever, that palladium was 4d10 with no 5s electrons, I would absolutely give you credit, all right? But during quizzes and exams, what I would expect you to do is you'd have 5s2 first and then 4d8, which would be the predicted N plus L rule. But N plus L rule does have its issues and stuff, and that's why your presentation was cool, because honestly, I'd forgotten that palladium was one of the weird ones, so yeah.
What, is there, I can't remember if you said there's a reason for that or not, because I remember seeing it and I was like, well, that doesn't look quite right, but it's whatever they said.
Good call. Honestly, no one really knows. You can justify with chromium, the first one, that the 4s electrons, one of them jumped ship to the 3d. So chromium should be a 4s2 3d4 by these rules, but it's actually 4s1 3d5. And you can kind of justify that, Lucas, because there's a little bit of energy to pair 2 electrons together. So if you take one of those and put it in the empty d orbital, that should be lower energy. That's cool. But in palladium's case, why would you take 2 out of 5s, which should be further, and put it in 4d? I don't have any justification for it, man. So there's still things to be done. Maybe one day we'll talk about the Lucas rule and how a better way to talk about how electrons goes through. Chemistry is not set in stone. Lots of work left to be done, and that's one of the big things I want to get across to all of you. So cool. Any questions on that? All right, so there are two ways to win on some of these elements, all right? Like, for example, with palladium, if you knew it was 4d10 with no 5s, awesome. If you called it 5s248, which is the predicted rule, awesome too, all right? And it has to do not with your understanding, but with chemists not totally figuring out all the details yet and stuff. So it's the state of research as of this moment. Okay, here's another kind of question you might see. Now, when you see questions like this, you have to assume that everything follows N plus L. But what neutral element, not an ion, but neutral element has this electron configuration? So see if you can figure out which of those elements has that electron configuration. And again, assuming that everything is set up right and all that jazz. Okay, so there's a couple different ways to do this, but probably the easiest way is, again, just to add up all of those superscripts, and that because it's neutral, the number of electrons that you count will equal the atomic number, the blue number on the periodic table. And if you do that, 2 plus 2 plus 6 is 10, plus 8 more is 18, 28 plus 2 would be 30. And if you look on the periodic table, that's going to be zinc. So this is the electron configuration for zinc. Now, I do want to talk about something else here, and it's the orientation of the last two subshells. It lists 3d10 before 4s2, and if you follow the off-bow diagram, remember it kind of goes this way, you fill in 3s, 3p next, but then technically 4s would be filled in before 3d. So sometimes you will see the 4s on the outside and not between 3p and 3d. Does anybody have any idea why chemists might like that sometimes? Yeah.
Finishes the threes and goes over the most nice.
It does put them all into the same shell level, which can be kind of cool. Here's a hint. In the oh, wait, that's from a different lab. Never mind. Do you think that that people use zinc metal more or zinc plus 2 ions? Like if you do a zinc supplement, do you think it's zinc metal or zinc plus 2? Yeah. Zinc plus 2 is a lot more common than zinc metal. So when you remove electrons from an atom, it always comes from the highest N. And 4N is higher than the 3s, the 2s, or the 1s. So if you see this kind of configuration, it's getting you ready to make the zinc plus 2 ion. So that's kind of the idea.
They use one zinc chloride isn't that a salt? So it's one used.
I believe that's right. Yeah. Nice job. So if you see the S's on the outside like that with a bigger N, it's basically helping the scientists to know that you're getting ready to make an ion and stuff. Good. Questions on? Sweet. Neutral tin is one of the elements that's used a lot. I'd like you to see which of these is the electron configuration for neutral tin. Tin is Sn on the periodic table. It's number 50. So see if you can figure out which of those represents the electron configuration for tin. Excellent. So, a couple of hints on solving this one. Tin number 50 has a lot more electrons, of course, than the other ones we've looked at so far. Tin is part of these 6 columns right here. Helium goes over here. And these 6 columns, which are 3A through 8A, no helium, are the p block, all right? So the outermost electrons in tin are going to be some kind of p electrons. And to figure out the number that goes inside it, before it, if you have an S block, which are these 2 columns on the right, and helium does go in there, or if it's a P block, these 6 on the right, you can use the period numbers to tell what number goes inside. So tin is in the P block, and it's in the 5th period. So tin is going to have 5 P electrons. Indium would be 5p1, it's the first column. Tin would be 5p2, antimony 5p3, etc., etc. So of these choices on here, we at least know it's going to be C or D, all right? It's a P block. Tin is in the 5th period, so it's going to have 5p electrons on the outside. So between the two 5p's, you can see it's krypton or xenon. All right. Well, to figure out the noble gas, you go backwards, and even though xenon is close, you have to go all the way back to number 36, which is krypton. So we would use krypton 5s2, 4d10 because they sneak in there 5p2. Xenon is in the future elements, if you will, so that would count. You have to go backwards to the most nearest noble gas. So this is an example of reading the periodic table. I mean, you could start down here, go 1s, 2s, 2p, 3s, etc. This is just another way that you can figure out these electron configurations. So, any questions on that? Okay. Here's another way to represent electron configurations. This is an orbital box notation. And I'd like you to figure out which element is represented by this orbital box notation. See if you can figure it out. Orbital box is great for magnetism. You can see in this atom, you have 2 electrons which are up with no downs. So that means that this atom will be a paramagnetic atom. So orbital box is pretty cool for that. This would have 2 unpaired electrons. Now, what we have here is neon core 3s2, 3p4. All right. So again, there's a couple of ways to do this. Using what we just talked about, period 3, the P's start with aluminum. So aluminum would be 3p1, silicon 3p2, phosphorus 3p3, and then sulfur would be 3p4. You could also count electrons. Neon is 10 plus 2 plus 4. That would be another way to get to sulfur. Any of these ways are fine. So, questions? Sweet. All right. Here's another neutral element configuration. Notice that there's F's inside. Also notice that the highest ends are on the outside because they're getting ready to take away electrons on one of these. But see if you can figure out what neutral atom, the neutral element, has this electron configuration. And again, on this one, I would probably try to read the periodic table, but you could also add the electrons up, whatever you want to do. When you see electron configurations, remember S's can hold up to 2, so that one's filled. P's can hold up to 6, so this one is not filled. But D's hold 10, F's hold 14, and G's would hold 18, etc., etc. So of all of these, this is the unfilled orbitals, unfilled subshell, and that means that's probably where the atoms stop. So one thing I would do is go to the periodic table again. Period 6 goes, if you go all the way over, the 6 P's begin with thallium, number 81. This is a 6P2, so I would think that this is probably lead. Now, if you're not certain, you can always count out. Lead has 82 electrons, and xenon is 54, yep. 54 plus 14 plus 10 plus 2 plus 2, you should find that it's lead, all right? So again, sometimes reading the periodic table is better. You can always do total electrons. I'm just trying to show you different ways to answer these, and you pick the way that works best for you. Lead is often plus 2, which means these electrons would go away, and it can be plus 4, which means these electrons would go away. If there's a tie between highest n, which are the first electrons out, take the highest n plus L, which means last one's in, first one's out. These would come out first, those would come out next, etc. Questions? Cool. Now, you can do ions as well. So what I'd like you to do now is find the electron configuration for phosphide. Phosphide is phosphorus with -3 charge. I would start with phosphorus and then add 3 electrons to see what you end up with. So phosphorus is a neon core 3s2 3p3. Phosphorus is right there. It's in the P block. It's in the third period. So 1, 2, 3, phosphorus would have a 3p3. So phosphide, you're going to put electrons in the lowest unoccupied spots. 3p3 actually has room for 3 more electrons. So phosphorus would then have not a 3p3 but a 3p6 configuration. So if the choice is there, answer A would be right. It's also equal to argon. In the old days, don't want to have just that. You want to put the nearest last noble gas, but I would take argon for an answer. But if you see that, just realize neon 3s2 3p6 is argon. Good to go. Notice here how the ions often take a noble gas configuration. Not always, but a lot of times, especially the main group metals and nonmetals. So phosphorus becomes like argon, the cool kid on the back of the bus I was babbling about on Monday. So, speaking of ions, now this one is a transition metal because it has some d electrons in it. This one rarely will be a noble gas notation, but you can still figure out what it is. So see if you can figure out, based on this information, which ion is represented. All right? Notice there are no 4s electrons. And for the 4s electrons, at the first level of transition metals, those are always the first ones out. So play around with this, see what you can think, and we'll talk about it here. So looking at this part right here, we have 3D electrons, 2, 4, 5, 6, 7 3D electrons. So how I would start this problem is the 3D group starts as scantium. So 1, 2, 3, 4, 5, 6, 7. Cobalt has a 3D 7. So it's not going to be anything before. So for example, iron is a 3D 6, all right? Unless it was some, no, it would be impossible to do that. So yeah, it has to be cobalt, nickel, something like that. And neutral cobalt has 4s2 electrons. But if you take away 2 electrons, i.e. making cobalt 2 plus, those are the first electrons to go. Highest N comes out first, and then the 3Ds would come out after that. So let's predict it's cobalt 2 plus. Now, nickel 2 plus right next door would have 1, 2, 3, 4, 5, 6, 7, 8 3D electrons and 2 4s. So nickel 2 plus, you would take out the 4s electrons, you'd be left with 3d8. So you'd have one more electron in one of those right there. So of all of these here, it's going to be cobalt plus 2. Rhodium, I didn't talk about, rhodium would be on the next level down. It would have 4d electrons, not 3d electrons, all right? And little lithium doesn't have enough electrons to be close to this, so. Questions on that? I'd like you to figure out which of these ions is diamagnetic. Which of them has just as many up electrons as down electrons? Maybe none of them are, but that's not true. One of them is paramagnetic. One of them is diamagnetic, excuse me, I said it correctly. And if you look at those 4, one of them is different than the other ones. The main group metals and nonmetals are groups 1A and 2A and 3A. Those are the metals. The main group nonmetals are the nonmetals over here on the right. And most of those will, when they become ions, will make a noble gas. They're the ones that want to be like the noble gases, the cool kids in the back of the bus. But the transition metals, lanthanides and actinides, when they make ions, they're not necessarily going to be like a noble gas. They can be, but they also is very unlikely. So if you look at these 4 possibilities, magnesium is group 2A, it's a main group metal. And all these other ones here are transition metals. So based on that alone, I would predict that magnesium would be a culprit. But you can confirm it because magnesium has a 3s2 outer configuration, and to make 2 plus, you have to take away those electrons. So of all of these, magnesium 2 plus is diamagnetic. And again, these main group metals, the main group nonmetals, when they make ions, most of the time they're diamagnetic. Most of the transition metals, lanthanides and actinides, are not diamagnetic, they're paramagnetic. 3d2, remember Ds have 5 orbitals, so you'd have 1 electron in each orbital, so that would be paramagnetic. Questions? Excuse me. Nickel plus 2, we talked about briefly earlier. We're going to revisit it here. Which one of these would be the correct electronic configuration for the nickel 2 ion? So nickel plus 2. And remember that the transition metals love to lose 4s electrons before 3ds. So see if you can figure out which of those looks right. symptom. Outstanding. So nickel, if you go backwards, the nearest noble gas is argon. So nickel, neutral nickel, would have an argon core. It would have 4s2 if calcium, and then 1, 2, 3, 4, 5, 6, 7, 8. It would have 3d8. So neutral nickel would have argon, 4s2, 3d8. But we want nickel plus 2. And those plus 2s always come from highest N, which means 4s comes out before 3d. And again, realize how weird that is. We filled 4s in first and then put in 3d, but the 4s's are the first ones out. That's the highest N part, and it's most interesting for the transition metals. So if you take those out, then it's going to have an argon 3d8 core. All right, highest N, highest F4 here comes out before 3. So it would be argon 3d8. Yeah, sure.
Do you have another problem methods where you have time?
Do we have what?
Another problem methods or we have time? It's 9:42.
It's 9:42. We have until 9:50. I can get through a few more, but there is a video link for this online and stuff. You bet. If you email me, I'll send it to you. Cool. Questions? Tin plus 2 is going to have a tin neutral core, and then you take away 2. So neutral tin, we're going to see, has, I'll just give you the answer here. Neutral tin would have a krypton core, 5s2, 4d10, 5p2. And when you make a positive 2 ion, you want to take away from one of the 5s first, leave the 4s alone. And in this case, 5p or 5s, 5p comes out. So if there's a tie between highest N, always take away from the highest N plus L, which means the last ones in are the first ones out. So tin plus 2 doesn't have any 5p electrons. Tin plus 4 wouldn't have any 5s electrons, all right? But you don't touch the 4ds unless you got to tin plus 5 or something like that. Okay, this is a good one to do. This is on periodic properties. I'd like you to tell me which of those elements has the biggest radius. And radius is like size of the atoms. So see if you can figure out which of those would be the biggest. So there's two types of trends. Anything with size gets bigger as you go left and down the periodic table. So what that means is helium in the upper right would be the smallest, and francium down here in the lower left would be the biggest. And you go left and down. And these are really cheesy, all right? They're not that good, but if you're in the hallway and you don't have your phone with you to check Google, then this is a nice way to predict. So of these elements, the one that's most left and down would be sodium. So we would predict that sodium would be the biggest atom of all of those. This works for ions as well. So if it was sodium plus, magnesium plus, sodium would be most left and down. Here's just another one, but this one is with ions. You don't need a table. You just want the one that's most left and down. So all of these are on the same period. So the one that's most on the left is phosphide. All right, so again, same kind of thing. Now, anions are always bigger than cations, but I won't ask you those kind of weird questions. You just want to look for the one which is most left and down. All right, so anything with size, left and down. And again, if you're publishing, you should look up the actual values to make sure that it's good to go. Now, this is an example of electron affinity. Electron affinity and ionization are the opposite, up and to the right. So of these elements, these 4 elements, JQ is just my stupidity showing, make a prediction as to which one has the largest electron affinity. Remember, it's up and to the right this time. So in the last example, sodium was most left and down. That's why it was biggest. On this one, we want the opposite. We want up and to the right. So sodium now is the most left and down. You go over to aluminum. Boron is above it. And then even more up and to the right would be carbon. So in this one, we would predict that carbon has the biggest electron affinity. And again, if you're publishing or writing an article, look these values up, all right, because these things can get pretty corny sometimes. But overall, as we talked about, it works pretty good. So if you don't have a table of values, then you can do this kind of thing. Questions? All right. And then this is the other kind of question you might see. It's something with order of, and it's either increasing or decreasing. This is an order of increasing. So you want to go up and to the right and put these elements in order. All right. So the lowest one will definitely be magnesium. And then after that, you can kind of follow the periodic table. So carbon would be next. It's more up and to the right than magnesium, definitely. Nitrogen is more to the right, and fluorine is the biggest one of all. So again, if it's increasing, you want biggest at the end, smallest at the beginning. If I was to ask a decreasing, you would just reverse it, all right? Decreasing, we'd have the biggest one first, smallest one last. Questions? All right. This really is all for them. As Michelle said, there is a video version of this, so you can watch it again where I talk about them a little bit more and stuff. I can send you that. It's under videos on our website, but I'm happy to send it to you. Any questions on any of this? All right. I will see you next Wednesday at 8:45 in this room. If you have questions on anything, please email me. I'll send you a link Monday morning with a link to the lab final. Have a great week.